All right, welcome ladies and gentlemen. This is video number 3, focusing on the relationship between E, G, and K, tying in electrochemistry with thermodynamics and equilibrium, aka there's a reason that the final 2 units of the year are the final 2 units of the year, because they all relate to one another, and there's simply certain things that we can't talk about until we've discussed equilibrium, and this is one of them. So just a bit of a reminder before we jump in with that a positive E cell value indicates a spontaneous process, right? A voltaic cell produces voltage, so it has a positive E cell. Negative E cell means a non-spontaneous process, and we can use this to actually work out activity series to work out which metal is more reactive than another metal. Metals love to be oxidized, right? That's what they do. And we can sort of use the list of standard reduction potentials to work that out. If you ever, by the way, see an E naught without the cell, it's just E naught, it simply means that it's not taking place in an electrochemical cell. So it's not necessarily a voltaic cell, but it's just like a normal chemical reaction. And we sort of drop the cell bit in order to refer to any given chemical reaction, one that might not be taking place in a voltaic cell. So if we consider this reaction right here and we want to work out if this is a spontaneous process, but we don't have access to delta G information, then we can use our list of standard reduction potentials to figure it out. In this process, the mercury is being oxidized and the silver is being reduced. So we would look up the standard reduction potential for the silver and the mercury, but we'd flip the sign on the mercury and then add them together. When we do that and we add them together, we get a negative voltage. So the fact that we have this negative E cell indicates that this process is non-spontaneous. It's not thermodynamically favorable. So we can use we don't just need to have delta G now. We can also use E in order to determine spontaneity. Now, maximum cell potential and spontaneity, specifically how do these two concepts tie together? Well, you should get that there's going to be a massive link between them because they are both commenting through their signs on whether or not the process is spontaneous. So they are absolutely directly related. There is a direct relationship between delta G and E. And it is through this formula right here. Delta G naught is equal to minus NF E naught. So let's take it, what do each of these things mean? Well, first of all, we already know delta G, we've seen this plenty of times. And considering units on delta G, obviously kilojoules per mole reaction. We're going to talk about N, we're going to talk about F, but E naught, we know what that is too, right? The unit on that is volts. And remember, a volt is, 1 volt is 1 joule per 1 coulomb. So what are the other things, the new things? Well, F is a constant. F is called Faraday's constant. And Faraday's constant, which is on your reference table, so this is not a value you need to memorize, is defined as 96,485 coulombs of charge per 1 mole of electrons. It's related to charge. So notice that we do have the Coulomb tie-in between the E naught and the F. What is N? Well, hopefully you remember that N stands for moles from PV equals nRT. In this case, N is not just moles of anything, it's moles of electrons, because we have moles of electrons here. And it's the moles of electrons that are transferred in the overall balanced equation. The way that you figure out N, if you don't have it explicitly given to you, is you have to consider the half reactions. The half reactions that are occurring in the overall balanced equation. If you separate it out and you manage to get the overall half reactions for this balanced equation, then you're going to look at the coefficient for the electrons, and that's going to give you your N value. Things that you do need to pay attention to in this formula. So units, units. You might be noticing that the unit for delta G is kilojoules per mole, and that the voltage in E naught, volts are defined as 1 joule per 1 coulomb, which means that you are going to have to convert. In this case, I strongly recommend that you convert delta G to joules, and keep the voltage as it is. So I'm strongly recommending that. But you cannot take your delta G that's in kilojoules and use it with your E that's in volts, because they are actually in a different unit from one another. So we have to make the units match. The relationship that we see through this equation is the same thing that matches already with what we know about the signs. If delta G is negative, right? If delta G is negative, we have a negative value up here for delta G, then we know that that's the same thing as saying that E cell is positive because they both mean spontaneous. So if you have a positive value here for E, and then you multiply it by this negative that we have sitting out in front, you will get the negative number on delta G. So this is sort of saying that, yeah, we do have to flip the signs, but we have this relationship. A negative value for delta G will give us a positive value for E cell, and they're both saying that the reaction is spontaneous. So big thing here, right? Delta G negative, E positive, spontaneous process. In terms of spontaneity, and then tying this in with equilibrium, a voltaic cell is functional until its potential reaches zero. When its potential reaches zero, that's when you have equilibrium. That's when delta G is equal to zero. And remember that equilibrium is defined as when the rate of the forward reaction is equal to the rate of the reverse reaction. If you think about this in the context of a voltaic cell, then you don't have an overall net push for the electrons to move from the anode to the cathode, because there's essentially equal push from both sides. There's nothing that's saying that the electrons should prefer to move to the cathode. Now there's equal push from both sides. The electrons simply don't move, and we don't manage to generate any voltage. That is actually when your battery is dead. When your battery goes dead, it's reached equilibrium. You have a system that has actually managed to reach equilibrium, where the rate of the forward is equal to the rate of the reverse reaction. So it's at this point when E is equal to zero and delta G is equal to zero that we're tying in our K, our equilibrium. Now, what we already know about delta G and K. We already know that delta G naught is equal to minus RT natural log of K, right? And we also already know from the previous slide that delta G is equal to minus NF E naught. We do not have this equation on our reference table, but the nice thing is that you don't need it. E is related to K. We know that E is related to K because both K and E are related to delta G. Well, okay, these are the same thing. So we can essentially say minus RT natural log of K is simply equal to minus NF E naught. All I did is set the two delta G's equal to one another because they're the same thing. They're delta G. If you lose the negative, because there's a negative on both sides, right? And then if you simply want to solve this for E naught, all we'd have to do is divide by minus NF on both sides. That would cancel out. And we wind up with this equation of RT divided by NF times the natural log of K is equal to E naught. And boom, we have a relationship, we have a mathematical direct relationship between the value for the equilibrium constant and the cell potential for a given system. R is the gas constant. We're going to use the same gas constant, 8.314 joule per mole Kelvin. T is temperature in Kelvin. N is moles of electrons. F is Faraday's constant. K is the equilibrium constant. And E is the cell potential. Pulling this all together, right, we have this equation right here. In terms of signs and magnitudes, well, if K is greater than 1, remember, if K is larger than 1, then that means that you have more products than reactants. That means that your forward reaction is the one that's likely to occur. That means that your forward reaction is the spontaneous process. If K is larger than 1, you take the natural log of a value that's larger than 1, you get a positive number. So this bit right here would be positive. There's no negative in the rest of this equation. It cancels out. So we wind up getting the positive E cell. If K is greater than 1, E will also be greater than 0. E is going to be positive. E is a positive value. If K is less than 1, then the natural log of a value less than 1 gives you a negative, it gives you a negative number. K is less than 1, so we wind up then with a negative value for E naught. Pulling all of this together, what's the huge critical piece here is to recognize that the sign on delta G, the sign on E, and the magnitude of K are all directly linked to one another. If delta G is negative, that means your process is spontaneous, which means that the K value must be greater than 1 because the forward reaction went on its own and generated more products than reactants. This will also mean that your E value must be positive because a positive E value indicates a spontaneous process. So, spontaneous, delta G is negative, E is positive, K is larger than 1. Non-spontaneous, delta G is positive, E is negative, K is less than 1. They're all commenting essentially about the same thing about the reaction. So we need to link these signs and these magnitudes together in our head. And the next slide simply shows the relationship between these three quantities. They are absolutely directly related. Sometimes I call this like the triangle of doom, right? It ties in thermodynamics, equilibrium, and electrochemistry, bringing all three together. If we have G and K, then we're using delta G equals minus RT natural log of K. If we have E and G, then we're using delta G naught equals minus NF E naught. If we have E and K, then we're using this equation, which this equation is not on your reference table, but you don't need it. Remember, this is simply a combo of this and this. You set the two equal to one another. That's all it is. That's all that formula is right there, which is actually why it's not on your reference table. It used to be, but we don't actually need it because it's simply the combination. So this is our big idea, and tomorrow you're going to be practicing with both the conceptual side of this and then doing some calculations with E, G, and K.